The equation of a quadratic graph takes the form y equals ax squared plus bx plus c. So, in my previous Geomaths video, we saw that the derivative dy over dx for the quadratic curve with equation y equals ax squared plus bx plus c is 2ax plus b. Now, we know the equation of a straight line graph takes the form y equals mx plus c where m is the gradient. So, as you can see here, the derivative dy over dx equals 2ax plus b is a straight line with gradient 2a. So, as we learned in the previous Geomaths video, we can differentiate a function with more than one term by differentiating the terms one at a time. So, differentiating the quadratic term ax squared gave us 2ax. And hence, the quadratic term tells you the slope of the gradient function. Now, let's take a look at a few examples. Find the gradient of the curve with the equation y equals 3x squared at the point 2, 12. So, as I said in one of my previous Geomaths videos, the gradient function can be used to find the gradient of the curve for any value of x. Then, in order to find the gradient at this point, first we need to differentiate to find the gradient function or the derivative. So, differentiating y equals 3x squared gives us the derivative dy over dx equals 3 times 2 times x to the power 2 minus 1. As we multiplied the constant 3 by the power 2 and then subtracted 1 from that power. Then dy over dx equals 6 times x to the power 1 equals 6x. Now since the gradient function can be used to find the gradient of the curve for any value of x, we can find the gradient of the curve with the equation y equals 3x squared at the point with the coordinates 2, 12 by substituting the x coordinate value, in this case 2. So dy over dx equals 6x. Then substituting the x coordinate value gives us 6 times 2 equals 12. So the gradient of the curve with the equation y equals 3x squared at the point 2, 12 is 12. Moving on to another example, find the gradient of the curve with the equation y equals x squared plus 4x at the point 1, 5. So first we need to differentiate to find the gradient function. Since there are more than one term, we need to differentiate the terms one at a time. So starting with x squared, differentiating x squared gives us 2x. Now 4x, here the power of x is 1, so let's say 4x to the power 1. Now, to differentiate, we multiply the constant 4 by the power 1 and then subtract 1 from that power. Then, 4 times 1 times x to the power 1 minus 1 equals 4 times x to the power 0 equals 4 times 1, as x to the power 0 equals 1. Then it's 4. So, dy over dx equals 2x plus 4. Now, to find the gradient at this point, we need to substitute the x coordinate value, in this case 1. So, dy over dx equals 2 times 1 plus 4 equals 2 plus 4 equals 6. So, the gradient of the curve with the equation y equals x squared plus 4x at the point 1, 5 is 6. Now, find the gradient of the curve with the equation y equals 3 plus 2x minus x squared at the point 1, 4. So, first we need to differentiate to find the gradient function or the derivative. Now, since there are more than one term here, we need to start by differentiating the terms one at a time. Now, starting with 3, differentiating 3 gives us 0. The constant term, in this case 3, disappears when you differentiate. Now, 2x. Here, the power of x is 1, so let's say 2x to the power 1. Now, to differentiate 2x to the power 1, we multiply the constant 2 by the power 1 and then subtract 1 from that power. So, 2 times 1 times x to the power 1 minus 1 equals 2 times x to the power 0 equals 2 times 1. As x to the power 0 equals 1, then 2 times 1 equals 2. Now, minus x squared. So, let's say minus 1 x squared to avoid confusion. Then, differentiating minus 1 x squared gives us minus 1 times 2 times x to the power 2 minus 1, as we multiplied the constant minus 1 by the power 2 and then subtracted 1 from that power. So, minus 2 times x to the power 1 equals minus 2x. Then, dy over dx equals 0 plus 2 plus minus 2x equals 2 minus 2x. Now, in order to find the gradient at this point, we substitute the x coordinate value, in this case 1. So, dy over dx equals 2 minus 2 times 1 equals 2 minus 2 equals 0. And hence, the gradient of the curve with the equation y equals 3 plus 2x minus x squared at 1, 4 is 0. Now, let's take a look at a few more examples. Find the coordinates of the point on the curve with the equation y equals x squared plus 5x minus 4, where the gradient is 3. Now, since we know the gradient function can be used to find the gradient of the curve for any value of x, first we need to differentiate y equals x squared plus 5x minus 4 in order to get the gradient function. Since I've already covered about how to differentiate quadratics in the previous examples and in my previous video, I won't go further into detail here. Now that the derivative dy over dx equals 2x plus 5. Since the value of the gradient is given as 3, we need to set the gradient function equal to 3 in order to solve the resulting equation to get the value for the x-coordinate at that point where the gradient is 3. So, setting the gradient function equal to 3, 2x plus 5 equals 3. Now, we can solve this to get the value for x. Then, 2x equals 3 minus 5, 2x equals minus 2. Dividing both sides of the equation by 2 gives us x equals minus 1. So, the x-coordinate of the point on the curve with the equation y equals x squared plus 5x minus 4 where the gradient is 3 is minus 1. Now, in order to find the corresponding y-coordinate, we can substitute this value of x to this equation. So, substituting x equals minus 1 to y equals x squared plus 5x minus 4 gives us y equals minus 1 squared plus 5 times minus 1 minus 4 equals 1 minus 5 minus 4 equals minus 8. And hence, the coordinates of the point on the curve with equation y equals x squared plus 5x minus 4 where the gradient is 3 is minus 1, minus 8. So, as I said earlier, for the quadratic curve with the equation y equals ax squared plus bx plus c, the derivative dy over dx equals 2ax plus b, where the derivative is a straight line with gradient 2a. Now remember, this straight line crosses the x-axis once at the point where the quadratic curve has 0 gradient. So, this is the turning point of the quadratic curve. So, in order to make this clear, I'll take the graph of y equals fx where fx equals x squared minus 2x minus 8. Now, this is the graph of y equals x squared minus 2x minus 8. I won't go further into details about sketching graphs as I've already covered about it in my previous Geomaths videos. Now, as you can see, the graph of y equals fx crosses the x-axis at the coordinates minus 2, 0 and 4, 0 and the y-axis at 0, minus 8. So, the graph y equals fx has a turning point at 1, minus 9. Now, on the same set of axes, I'll sketch the graph of y equals f dash x. Since I've already differentiated x squared minus 2x minus 8 in the previous video, I won't go further into detail here. So, when fx equals x squared minus 2x minus 8, the derivative f dash x equals 2x minus 2. So, the graph y equals f dash x, which is y equals 2x minus 2, is a straight line with gradient 2 and crosses the y-axis at minus 2. Now, this is the graph of y equals f dash x, and the graph y equals f dash x crosses the axis at the coordinates 0, minus 2 and at 1, 0. So, here at the turning point of the graph y equals fx, the gradient is 0. Now, we know the gradient function or derivative can be used to find the gradient of the curve for any value of x. And since the gradient at the turning point 1, minus 9 of the curve y equals fx is 0, the derivative of fx, that is f dash x, equals 0. So, f dash x equals 2x minus 2. So, when f dash x equals 0, 2x minus 2 equals 0, then 2x equals 2 and x equals 1. That is, the graph y equals f dash x crosses the x-axis at x equals 1. And hence, the x-coordinate of the turning point of y equals fx is the same as the x-coordinate of the point where the graph of y equals f dash x crosses the x-axis.